Hi, my name is Martin Klein, and I am at the Los Alamos National Laboratory. Today, I would like to talk about Memento Tracer, our novel and innovative web archiving approach that aims at balancing scale and quality. This work is in collaboration with Herbert van de Sompel, as well as current and former members of the prototyping team at Los Alamos, and current and former members of the Web Science Digital Libraries Research Group at Old Dominion University. So when we talk about web archiving issues, we frequently talk about scale, web archiving quality, and of course also resource boundary, meaning which bits and pieces of a web resource are in scope for our web archiving efforts. Well, fortunately, for web archiving, we have a fairly diverse landscape, and we know that there are several different players that excel at some of these issues. The Internet Archive, for example, is really good at scale, as we know. Right? Brewster Kahle, for example, almost 3 years ago, tweeted that the Wayback Machine is currently offering almost 660 billion web objects. So that's a huge number. That's great in terms of scale. Only a year later, he tweeted again that we're now at 750 billion web objects. And roughly a year and a half ago, he tweeted that we're now almost at 900 billion URLs. So that is scale. That is huge. That's a great number. However, how about fidelity or web archiving quality at the Internet Archive? And I'm sure everybody here has their own examples of how the capture quality is not necessarily always what we'd like it to be in any web archiving environment, including the Internet Archive. One example that I show here on this slide is the numerous captures of the news website CNN.com that are in theory available in the Internet Archive could not be replayed for the longest time because of some JavaScript oddities. And as far as I understand, this problem is now fixed, but for a long time, these resources were not available for replay. So we couldn't even assess the notion of archival quality in this particular case. But as we also know, there are other players in this domain that are really, really good at fidelity. The incredible web recorder tool, for example, really excels at fidelity and high quality web archiving captures. As shown on the right-hand side of this slide here, Jasmine Mulligan from Stanford University Press, for example, was motivated to capture born digital manuscripts that Stanford University Press had published. And she found that Web Recorder really was the only tool that faithfully could capture these digital resources. So just an example of where Web Recorder excels at fidelity and is one of the few players in this realm that can take care of those resources. But how about scale when we're talking about Web Recorder? Well, it is not designed to capture 900 billion URLs, right? I think that is fair to say. It's a human driven web archiving approach. Yasmin, for example, said that it took her roughly a week to capture the entire manuscript of the Enchanting the Deserts resource that Stanford University Press publishes. So there's that. And Jasmine actually, she published a blog post of which I put the URL on the slide here, describing her efforts in this context. I encourage you to go read it. So Web Recorder is not necessarily made to match the same sort of scale that the Internet Archive has, right? And how about the resource boundary? Let's say you have a URL of a slide deck, a SlideShare presentation, a slide deck as shown here on the left-hand side of this slide. Would you be satisfied if this is all your capture framework got? Probably not, right? Because it is a SlideShare presentation, in this case, containing 96 slides. You would probably want your archiving framework to capture each and every single one of those slides as well. Well, how do you do that? How do you explain to your web crawler to click on this white triangle indicating to navigate to the next slide? And how do you tell your crawling framework to do this 96 times? And how do you tell your crawling framework to stop at some point, right? So those are difficult questions. You may also want to obtain a download copy of those slide decks, which means that the crawler need to click on the download button there. But how do you know that? How does your crawler know that? GitHub is another good example to explain the boundary problem. If you're crawling a GitHub repository, would you want all the files contained in that repository as shown on the left-hand side of the slide? Yeah, probably. But how about all the issues in the repository or the wiki that may be part of that repository? Well, that probably depends on your curatorial decision, right? Or would you like a zip file containing all the files of that repository? Yeah, maybe, probably, right? But then your crawler needs to click on the clone clone or download link, and immediately thereafter, as shown on the right-hand side of the slide, on the download zip button. How does your crawler know that? So all these are difficult questions, and all these questions motivated us to develop the Memento Tracer framework. And of course, we're not the only ones or the first ones thinking about this issue, right? Our efforts were really inspired by previous and ongoing issues, efforts, logs being one of them, right? Where we see heuristics being applied for different providers of scholarly content. Web Recorder, as mentioned before, of course, with its manual recording of web resources concept really inspired us there. And we also are aware of previous and ongoing efforts to try to automate certain interactions or behaviors on the web, such as browser or browser tricks. So how does Memento Tracer actually work? Let me try to explain at a high level. Let's assume, as shown here on the left-hand side, a curator navigates to a web resource. The curator can then trigger the Memento Tracer browser extension, and the curator can start interacting with the web resource in a way that these interactions indicate which components of the web resource, which bits and pieces are in scope to be archived by the web archiving framework. So for example, the curator could indicate that certain links should be followed, or that an area of the page that contains a number of links are all in scope. The curator could also indicate that the page should be scrolled, really, because upon scrolling dynamically, additional content is loaded that is all in scope to be archived. So these sort of interactions is what the curator can record in what we call a trace. These interactions are recorded by means of browser events into a trace. The curator can save that trace, and jumping to the right-hand side of this diagram here, this trace then can be used as basically a set of instructions for a crawling framework. So, for example, a headless browser controlled by a WebDriver, let's say Selenium, would use this trace as input and would be able to reproduce and re-execute all interactions that the curator had recorded in a trace. So the crawling framework would know which links to click on, where to scroll, which navigational elements to execute, for example, to discover resources that otherwise, prior to that navigation, were, for example, hidden. Right? So how does this framework address issues of the boundary, issues of quality, or issue of scale? Well, the boundary issue is probably obvious. The curator indicating which bits and pieces are in scope. So that's how we define the boundary of the resource is very well defined. How about quality? Well, our headless browser shown here on the right-hand side is executing the trace, is re-executing all interactions, and therefore addressing the quality issues, because even, as I mentioned, even complex interaction and navigation elements can be re-executed by this browser-based archiving framework. But how about scale? Well, scale is really addressed in two different ways. A, the trace that the curator created for a particular resource, if this resource falls into a class of resources, it can be reused. Meaning, if I create a trace on a slide deck in SlideShare, this very trace can be reused for all SlideShare presentations that my crawling framework encounters during crawling. Or another example, if I create a trace on a GitHub repository, on a specific GitHub repository, the very same trace can be reused for all GitHub repositories that my crawling framework encounters. Right? So with this sense of reuse, we can address scale to an extent. Another way we can address scale is by what is indicated here in the center, in the middle of this slide, is I can share my trace. So we don't all have to create the same trace individually. We can share created traces. We can version traces. We can edit traces. For example, if a user interface has changed and our trace for a particular platform, GitHub, for example, needs to be updated, we can do this collaboratively. So it's another aspect of how scale can be addressed. So unfortunately, I don't have time to live demo Memento Tracer, but I have pre-recorded a number of videos that I invite you to check out for this. For example, I have a video for how to create a trace on a GitHub repository or on a slide deck. And then, of course, also on the bottom here, a video of how our demo crawling framework can be utilized with the traces input that will then crawl the resource of interest and provide a WAC file based on our trace that can either be replayed in the browser or we download it for offline replay. So what's the current status? We have, as I mentioned, implemented Memento Tracer in form of a browser extension, and several different types of interactions can be recorded. As indicated, single clicks can be recorded. We can identify a particular area on a web resource, on a web page that contains, for example, a number of links that are in scope. We can indicate that the crawler needs to repeatedly click on a particular link, and we can identify a stop condition for this repeated click, which comes in very handy for pagination, for example, or for slides as shown earlier. We can define a scroll event, so how often, how far, basically, we would like the crawling framework to scroll the page. We can identify hover events, for example, to maybe discover new resources that otherwise are hidden. And we can nest traces for more complex scenarios, basically. And so I alluded to some of this already. And so just to summarize how Tracer is addressing notions of scalability and quality. Given that we can reuse a once created trace to apply to the same to all web resources of the same class, for example, all GitHub repositories, all SlideShare presentations, it's a huge factor for scalability. And of course, traces can be shared as well for versioning, for example, to make this more efficient. Given that our trace is executed in a browser-based capture framework as a set of instructions to replay our interactions, that's how we really address quality here. And of course, the resource boundary is explicit in a trace. So we can guarantee that all the resources or the bits and pieces of a resource that are in scope are indeed captured. And of course, there's always a bit of a trade-off, right, between performance and quality and scale and those sort of things. And we actually, in fact, a couple of years ago, ran a set of experiments to measure and analyze Memento Tracer, and I put the URL of the preprint on this slide that shows the tracer is performing very well when it comes to scale and quality at a very small overhead in terms of, for example, compute time. Obviously, Tracer is not perfect or not complete yet, right? There are a number of issues that we still need to address. The language, for example, in which the trace is currently stored is just something that we came up with. This is not standardized in any way, which means that beyond our crawling framework, other crawling frameworks currently cannot execute the trace as a set of instructions. So we're very interested in standardizing this language to enable this level of interoperability between different crawling frameworks. It's not a solved problem yet of how to best share these repositories amongst peers. And I'm sure there are also limitations for the browser event listeners that cannot certainly capture some interactions, or there are also surely interactions that we haven't thought of yet that should be in scope or should be able, that Tracer should be able to capture. Currently, the identification of the matching between a trace and a resource to which this trace is applicable is done by means of URI patterns. And surely that's not the best solution. There's room for optimization as well. So if you're interested and you'd like to see Memento Tracer in action, I would refer you to our pilot available at myresearch.institute, where we used Memento Tracer to create traces on several different scholarly productivity portals and platforms, and archived scholarly artifacts from a number of scholars for almost 2 years. So this platform allows you to replay and download works that are based on traces that we've created, where we made the curatorial decision of which bits and pieces of these scholarly productivity portals are in scope. GitHub, Figshare, SlideShare, Publons are examples of scholarly productivity portals for which we have used Tracer, and I invite you to check that out on our pilot here. So this concludes my brief presentation today. I really appreciate you zooming in. Please do not hesitate and get in touch if you have any questions. If you'd like to discuss our approach, if you'd like to collaborate on our approach, we're always happy for collaboration. So I really appreciate your time today, and enjoy the rest of your day. Thank you. Bye-bye.